Okay, so we are continuing on with how to find antiderivatives. We just did basically the reverse power rule. If you are trying to integrate a variable to a power, you just add one to the variable and add one to the exponent, and then divide by the new exponent. Examples here. Okay, so how do we integrate a combination of power functions? So this is pretty similar to how we did derivatives. It's much easier to break this up into different terms and then deal with each one of them one at a time. So on this slide, you can see worked out, I just broke up this fraction into 3 different terms. And then once you do that, you just get 3 separate integration problems that are just power functions. And now you can use the reverse power rule that we just saw, add one to each exponent, divide by the new one. And so it comes out pretty nicely. So why don't you go ahead and see if you can figure out the answer, and the solution will be on the next slide. There you go. So notice that we only needed one constant of integration here. So technically each of those integrals we did will produce its own constant. So then we might have 3 constants, but then you can just add those 3 constants together and make them into a super constant. So even if we are integrating several different pieces of a function, so maybe there's multiple integral signs, integration signs in the problem we're working on, we're still only going to write the constant of integration once. So this family of functions, just has one constant of integration. So when we look back on this slide here, notice that in between, so from this step to this one, I pulled the 2 out of the integral and put it out front. So that's allowed because if you think back to what we're actually doing, so let's say I had a function, let's say this is square root of x, and then this function is 2 square root of x. If I'm trying to find the area underneath 2 times square root of x, I can either, so what I can do is find the height of each of the rectangles underneath 2 square root of x and add them all up. But if I found the area underneath just square root of x and then multiplied that total area by 2, I'd get the same number, because each of the heights of the infinitely skinny rectangles on 2 root x are double the height of the rectangles on root x, so the area you're going to get is double. So that is why you can pull a constant out of the integral operator. Because you can multiply a height by 2 and then find the area underneath it, or you can find the area and then multiply by a constant. You're going to get the same thing. So we're going to actually use that a lot as a technique when we start doing the reverse chain rule. But constants can be inside the integral or outside the integral. Just like, if I were trying to take the derivative of 3x to the 4th, I could think about that as I'm taking the derivative of this whole expression, 3x to the 4th, I'd get 12x cubed. Or I can think of it as I'm going to pull the 3 out front and then do the derivative of just x to the 4th, and then I'd get x cubed, and then I multiply by 3. So same deal, we're allowed to do that. Okay. All right. So this is a slightly different, okay, so skip the slide. Okay, so the process we've been doing here to find an antiderivative is called indefinite integration. So indefinite integration is a problem where you have an integral sign, but there are no bounds of integration on it. You're just trying to find the general antiderivative of the given function. So here you get x cubed over 3 plus c. So there are no bounds of integration. That's just asking us what is the antiderivative of this function that you gave us. If you think back to the problems we've been doing for last week, that we're trying to estimate areas between 2 values on a certain interval, we're trying to find the area underneath a function in between 1 and 3, when x equals 1 and x equals 3. That's a different problem, technically speaking. we're trying to find the area under some specific numbers. That process is called definite integration. So integration when you have bounds from A to B, and you're trying to find a specific area, not just the general antiderivative. That is called definite integration. In order to find the definite integral, or find the exact area under a curve, the first step is to find the antiderivative, which we've been practicing here. And then, as we know from the fundamental theorem of calculus, the area underneath a derivative function is just equal to, so we saw the fundamental theorem of calculus earlier. It's just the antiderivative, the difference between the antiderivative evaluated at B and A. So if we can figure out the antiderivative, we just need to evaluate it at the bounds of integration. So here's an example on the next slide. So we have this function, x squared plus 2x plus 3. It's a quadratic. We're trying to find the area underneath the curve. So step one, step one, find the antiderivative. So this is just like the problems that we've been doing up till now. What is the antiderivative of x squared plus 2x plus 3? I'll give you a second to put that in. So the new part now is going to be to find the antiderivative evaluated at 3 minus the antiderivative evaluated at 1. So antiderivative. I'm going to get x cubed over 3 plus 2x squared over 2. So that's just going to simplify to x squared plus 3x plus c. Right? And then I am going to evaluate that. So just some notation here. So the integral of x squared plus 2x plus 3 in between x equals 1 and x equals 3 is equal to the antiderivative Okay, and then so here's some new notation. Sometimes this will be written as a backward-facing bracket, or sometimes just a vertical line. That's not what I wanted. That symbol means evaluated at 2 points, and then you take the difference. So this is read as x cubed over 3 plus 3x squared plus x squared plus 3x plus c, evaluated 3 minus evaluated at 1. So that's just some notation after you've done the antiderivative and you're working with the antiderivative or original function, however you want to think about it. This notation is how you carry along the bounds of integration. So go ahead and figure out what the antiderivative evaluated at 3 as, what is the antiderivative evaluated at 1, and then what do you get when you take the difference. All right, so here is the solution. When we plug in 3, we get 27 plus c. When we plug in 1, we get minus 4 1/3. Oh, God, a mixed number. I hate myself. It's also known as 68 thirds. So just a couple things to notice here. This notation that I was talking about here, evaluated at, so that little symbol is read as evaluated at. And notice what happens to the constants of integration when we are doing a definite integration problem. So we had a plus c in this parentheses, and then when we subtract the antiderivative evaluated at the second value, so here we were evaluating at 3, and then we're going to subtract the antiderivative evaluated at 1, you get a plus c and a minus c, and the c's cancel out. That happens for every definite integration problem. So a lot of times, if we're doing a definite integration problem, the c's will always disappear. So your answer will not have a c in it for a definite integration problem. And that's because we are finding an actual area in between 1 and 3, right? So there's not a question of, oh, well, there are a lot of different functions that could have given me this derivative or something like that. They're just an actual area. And any antiderivative in this family of functions would give the same area between these curves. That's actually a pretty interesting topic as well if you think about it. Okay. So here's an example for you to try. So go ahead and first find the antiderivative, and then we will evaluate. Okay, so go ahead and put that in. I'm going to pause it and put the answer in. Okay, so here's the antiderivative, negative x cubed over 3 plus 4x, evaluated at 2 and negative 2. So go ahead and figure out what this is equal to, evaluate at each point, and then take the difference. Okay, so here I just plugged in the numbers, and the answer you get is 32/3. So the area underneath the function negative x squared plus 4, in between negative 2 and positive 2, is 32/3 units. I drew a little graph down here to graphically illustrate what we're doing. So the problem that we were trying to do is to find the area underneath the red curve in between negative 2 and 2. And then because of the fundamental theorem of calculus, what we know is that that area should be equal to the difference in the y-coordinates of the antiderivative evaluated at 2 when x equals 2 and x equals negative 2 at the bounds of integration. It's actually kind of cool. So if you think about the red curve, as you start at negative 2 and you're moving in the positive direction, you're accumulating area, you're picking up area, you're picking up area, and that is what's causing the value of the antiderivative to increase. So as we're getting more area under this curve, the antiderivative is increasing, right? So the derivative is positive here, so the original function or antiderivative is increasing. And it keeps increasing until we get to 2. The derivative is equal to 0 there, and that's when the original function reaches a turning point. And so after that point, we're actually adding negative area if we were to keep integrating, and that's what's dragging the value of the original function down. And actually, if you check, if you plug in negative 2 and 2, you get the y-coordinate at on the antiderivative for at negative 2 is negative 16/3, and then you get positive 16/3. And we take the difference, that does in fact give you 32/3, which is the area under the red function. That's kind of cool, since this the red function is symmetric over the over y equals 0, so is the antiderivative. There's a lot of kind of cool little properties if you think about it. Okay, let's see what we've got time for here. I think I'm going to start getting into other types of functions besides just power functions. We've already covered this. Yeah, so I'm gonna do other types of functions in a different video. This is a good grounding in how to do indefinite and definite integration. All right, thanks, y'all.